Most of us picture space as a quiet, starry expanse, a majestic, mostly empty void. Then, NASA points the Solar Dynamics Observatory at our sun and finds a glowing, highly active jack-o'-lantern face staring back. Or consider asteroid 2015 TB-145. When this 2,000-foot wide chunk of rock drifted past Earth right around Halloween, its physical dimensions mapped perfectly to a giant human skull. Astronomers later identified it as a dead, burned-out comet. We project monsters onto these inanimate celestial objects because of a human evolutionary trait called pareidolia. Our brains are aggressively hardwired to recognize faces and familiar patterns, even in completely random noise. Beyond the familiar shapes, these anomalies mark the point where our biological intuition ends and the actual mechanics of a universe operating on a non-human scale begin. Pareidolia explains why a burned-out comet looks like a skull, and it explains the exact mechanism behind our grinning sun. That glowing orange face is an outline of concentrated electromagnetic activity. You are looking at active regions of the sun's surface, twisting together and emitting massive amounts of intense ultraviolet light and energy. Our senses mislead us with audio, too. Because space is a vacuum, there are no physical molecules to compress and carry acoustic sound waves to your ear. Between the stars, it is completely silent. But we can detect energy in other ways. When NASA's Juno spacecraft crossed into Jupiter's massive magnetic field, it recorded intense waves of electromagnetic energy. To study the data, scientists translated those invisible cosmic events into audible frequencies, creating a shrieking, high-pitched sound. We interpret these sights and sounds as haunting because our limited human senses are trying to process raw, unfiltered data from environments we were never built to survive. Take the concept of absolute darkness. On Earth, shadows move with the sun, but near the poles of our moon, there are deep craters trapped in permanent shadow, with temperatures hovering near absolute zero. This 3D model shows how the specific geometry of the moon's tilt prevents sunlight from ever dropping below the elevated rims. The floors of these polar craters haven't received a single ray of sunlight in billions of years. Over on Mars, changing seasons trigger a completely different extreme. As the Martian spring arrives, temperatures rise just enough to warm frozen carbon dioxide buried beneath the surface, causing it to sublimate directly from solid ice into a gas. This cross-section illustrates how expanding gas gets trapped under the crust. Pressure builds steadily beneath the surface until the soil ruptures. When the trapped gas shoots upward, it blasts darker subsurface dust outward, scattering it across the landscape in deep spider-like radial patterns. And for a true thermodynamic extreme, look at exoplanet HD 189733b. It features atmospheric winds whipping across its surface at 7 times the speed of sound, driving sideways rainstorms made entirely of molten glass droplets. None of these environments have a hostile intent. They are the logical, unfeeling outcome of extreme heat transfer and pressure, operating without the buffer of a temperate atmosphere. Gravity acts as an equally brutal sculptor, capable of physically scarring planets and moons. You can see the evidence clearly on Miranda, an icy moon orbiting Uranus. Miranda looks like it was patched together from spare parts. Its mismatched surface is covered in deep craters, in high ridges, and extreme cliffs, the scars of intense tectonic activity driven by gravitational tidal forces constantly squeezing and pulling the moon. We even use the permanent pull of gravity to manage our own dead technology. When human-made satellites reach the end of their lives, if they are too far out to burn up in the atmosphere, they are pushed outward into a graveyard orbit to safely circle thousands of miles away from active spacecraft indefinitely. That the ultimate gravitational anchor in our neighborhood sits at the center of the Milky Way. This image, captured by the Event Horizon Telescope, shows the glowing gas surrounding a supermassive black hole, an object with gravity so dense that not even light can escape its pull. This visualization shows what happens when matter gets too close. The gravitational pull on an object's near side becomes exponentially stronger than on its far side, stretching it vertically into a long, thin strand in a process called spaghettification. From the torn tectonic cliffs of icy moons to matter being stretched into ribbons, gravity dictates the structure of the most violent and active phenomena in the cosmos. We look out into the galaxy and find sideways storms of molten glass, translate magnetic radiation into shrieking audio, and locate gravity wells capable of stretching stars into a single thread. Space operates as an unfiltered physics laboratory. Out there, the laws of thermodynamics, electromagnetism, and gravity play out to their absolute maximum limits, completely unrestrained by protective atmospheres. Here on Earth, we sit safely behind a thick atmosphere and a magnetic field that shields us from the worst of that violence. We experience stable seasons, liquid water, and gravity that keeps us anchored without tearing our tectonic plates apart. After seeing the glass rain and the lightless craters, the true goosebumps come from realizing just how narrow the window for stability really is. In a galaxy defined by chaotic extremes, our quiet, balanced environment is the outlier.